the delay.
All right, so let's get this show on the road. I'm Steve Elner, and I'm going to be acting as the host or moderator or whatever for today's colloquium, but I want to emphasize that I'm not the one who invited Jonathan. Jonathan was invited by the CAM graduate students. So he is this semester's People's Choice CAM colloquium speaker, a very honored position, and one which I think he fully deserves. Jonathan and I emerged from the same nest, Simon Levin's research group, although I was long gone by the time Jonathan arrived. He's currently in the biology department at McMaster, but if you read the blurb about his talk, you know that he did not follow a straight and narrow path to get there. Detouring to be in the Peace Corps, a Nader's Raider, a rabble-rouser in Taiwan, before settling down as an academic. He's a bit of an iconoclast. He told me once that he likes to work on diseases that other people are ignoring. Today, that is very much not the case. He is going to be talking about the disease that everybody is thinking about. If you have questions, please use the raise hand feature in the participants list. I'll be monitoring that. While the talk is going on, please mute yourself, but feel free to leave your video on so that Jonathan will feel like he has an audience. And after the talk, we will all be heading over to the CAM chat room to continue the conversation. And this is being recorded, both the talk and the question and answer afterwards. So with that, Jonathan will tell us about time distributions and coronavirus control.
Thank you very much. I do encourage people, if you feel I should be interrupted for clarification, to sort that in the chat, and either you or Steve can just interrupt me. If it's a deeper question, of course, I'll be delighted to hear it at the end. I will not personally see, I think, if you raise your hand, because I have a full screen thing going on here. So what I do is dynamical modeling of diseases. I often spend some time talking about that. I think this audience knows what dynamical modeling it is, but I get really excited about the idea that dynamical modeling is the way that we go from one scale to another. In this case, from the scale of a single event, one child foolishly touching another child, to continental and decades-long patterns of, for example, reports of measles. Can you see my mouse when I move it around? I'm pointing now between the two children. And somebody can tell me whether you see it or not, because I'd like to know going forward.
Yes.
Thank you.
Yes.
So what are some of the current questions that people have about COVID? And I guess, how do they interact with my ongoing modeling, which has come to be more and more about time distributions? So one question is, how far and fast would COVID spread if unchecked, if we adopt the Great Barrington Declaration, or if we had ignored it at the beginning? How hard will it be to eliminate COVID? What will it take to reach or go beyond herd immunity, whether by vaccines or by control? And how are we doing in a particular place in time? So here, the particular place in time is here for me and now in Ontario. These are data curated by Mike Lee from McMaster, showing that over the last 6 weeks, not only have the notifications been going up, notice not from zero, but also the proportion of tests that are positive have been going up. How do we model disease spread will be familiar to a lot of you. We use compartments. We imagine that people are born into a compartment where they're susceptible, and they can move into a compartment where they're both infected and infectious, but they can only do this if they meet another infectious person. And I love this diagram. This diagram by itself with the dashed blue arrow encodes a lot of assumptions, and you can make a lot of conclusions without even going to a formal model. I'll try not to get sidetracked into that, but the basic assumption is that black arrows get followed automatically unless there's a blue arrow there. And the simplest way to turn this into something you can actually solve on a pad of paper to some extent or run on a computer is with an ordinary differential equation model. But the ordinary differential equation is only one possible instantiation, only one possible way to implement the model. And so you do that and you find I've added now births and deaths, you may have noticed as I was zooming past the equations. And by the way, these slides are available online. I tried to put them in the chat, or maybe somebody will put another version of the link in a few minutes if you want to look at them now or later or during the question period. But you get some interesting dynamics just from this simple model. You see that a lot of diseases have a tendency to invade very fast. There's a tendency to oscillate. There's a tendency for the oscillations to be damped. There's a long history of modeling specific diseases with specific boxes. So here I've added a very traditional box for E, meaning exposed to the disease, but not yet infectious. Here's a set of realistic compartments that was made up early in COVID that were meant to be specifically about COVID with asymptomatically infected people. I'm trying to make this talk more mathy than the usual talk. So I said asymptotically instead of asymptomatically. And then various degrees of severity and various possible outcomes for the person. This is to remind me, the ODEs are not the model. This is the model. We can instantiate it with ODEs. We could instantiate it with a discrete time model. We could instantiate it with everything being smooth and continuous in time, but imagining that our individuals are individuals. And if we do that, we find even at the scale of a city that the interaction between the dynamics of the disease and the dynamics of immunity gives us macroscopic fluctuations just from individual level stochastic, what we call demographic stochasticity. So the model is not the ODEs. And another way to look at it, which I'm going to use heavily for the rest of my talk, is what's called the renewal equation framework. So in a renewal equation framework, it's all about this integral here. We imagine that the number of new cases, so I of t is incidence. It's the number of people who get infected today, and it's related to the number of people who are susceptible, and it's an integral over the people who are infected in the past. So this K of tau says, on average, if you were infected 3 days ago, are you likely to be infectious at all, multiplied by how infectious are you likely to be? And this is a really simple, powerful, and fairly general way to ask a lot of disease questions. Here's the terminology, which I accidentally explained before showing you. We sometimes treat S as a constant, and then we can linearize this and get simple results. So here's a graphical view of the same thing. These are estimates for Ebola, smoothed into continuous time, but the idea is that as I get infected with Ebola, I reach a certain peak infectiousness. The black line is the kernel, and we often break the kernel up into a distribution. So this blue line is the kernel normalized into a distribution, and then we multiply that by capital R, the effective reproductive number, and that's the expected number of new infections per infection under the current condition. And that's a critical number that a lot of you, I'm assuming now that since you're all mathematicians during COVID, you've heard about R or R0 or the basic reproductive number. And I'll mention that the renewal equation, in addition to being simple and in general generalizes most of the box models that you would think of. And you can prove this in various degrees of detail using something called the linear chain trick. We have a paper with David Champerdon, which I think I forgot to cite, that gives some specific examples of how to do this. But if I create ODs describing what happens after people get past the blue arrow, I can integrate those and put them into a renewal equation. And I can do it for most box models, including most of the box models that people are in fact using for COVID. So I'm trying to not go too fast. I'm trying to engage people. I put this picture of a bus in here to make myself try to engage you people, and now I'm trapped. So the question is, and this is going to be an analogy with going from box models to generation intervals. So what's a generation interval in a disease model? Those of you who've thought about disease models might think that the generation interval is equal to the infectious period for a simple model, or the exposed period plus the infectious period for a more detailed model. And that's both right and wrong. And to understand that, I'm going to ask you, if buses come every 10 minutes on average, and I go to the bus stop, how long on average do I expect to wait for a bus? Does anybody want to offer a verbal answer? It's not a trick question in the sense that I'm not going to say you're wrong. In fact, I'm not sure. Well, there are some wrong answers. How long on average do you expect to wait for a bus? Assuming everybody's scrambling for their unmute button.
There's a few of us that teach this stuff, so it's a bit cheating. I'll keep quiet for a bit.
No, please cheat. Please cheat. I got a lot to get through.
Okay, a bit more than 5 minutes.
Okay, so 5 minutes or more than 5 minutes is one of the two correct answers I was expecting. If the buses come every 10 minutes like clockwork, then you would expect to wait 5 minutes. You get to the bus, the waiting interval is about 10 minutes, and you get to the bus in the middle, so that's about 5. The other correct answer, which is not rare to get, is 10 minutes. Maybe we're assuming it's a memoryless distribution. Maybe it doesn't matter how long you've been waiting. The buses just leave at random. And the part of this that I find really interesting is, let's assume it is a memoryless distribution. Let's assume that buses leave the bus station or leave whatever point is most relevant to you every 10 minutes on average, but with no memory of when the last bus left. Then I can say, well, obviously I get to the bus stop, I expect to wait 10 minutes. But there's a paradox here, and it's not a completely trivial paradox, because it's also been on average 10 minutes since the last bus came. If I look backwards in time, it's time homogeneous. So if I assume that buses come every 10 minutes on average without memory, I can conclude that buses come every 20 minutes on average. And this, I claim it's a non-trivial paradox. It's not a very hard paradox, but non-trivial. I'm not sure to how many of you it immediately occurs the answer, but it's related to, well, it's related to the mean of a self-weighted quantity. It's the difference between how long it is between buses for the average bus, which is 10 minutes, and how long it is between buses for the average person who arrives at the bus stop at a random time. If I arrive at a random time, I'm more likely to arrive in a long interval than a short interval. So in fact, my mean bus waiting time is related to the mean of a self-weighted quantity. That is to say, the bus waiting time. And in many contexts, disease contexts, we see similar self-weighted means. The infectious period of an infector, or the activity level of a random interactor. Some of you will have heard a meme from a few years ago that your friends on average have more friends than you do. And if you're an average person, that's correct because of this same phenomenon. I'm going to try not to get trapped because I feel like I'm already behind time. But the mean of a self-weighted quantity is equal to the mean of the original quantity times 1 plus the squared coefficient of variation. And so the time until the bus comes on average could be 5 minutes or anything at all larger than 5 minutes, right? So it could be 10 minutes. If it's a memoryless thing, then kappa is going to be exactly 1, and it's all very beautiful. But we could also, like here in Hamilton, Ontario during rush hour, kappa is bigger than 1. And on average, you actually wait longer for a bus than the average period during, between buses. And that's partly due to idiotic scheduling, but mostly, of course, due to traffic congestion. Going back to infectious periods, and I hope I have a slide for it, a generation is actually the latent period, that is to say the time I spend in box E until I become infectious, plus what we call an infectious waiting time. And the reason I stress this so much is that there's a big history in the disease modeling world of conflating the infectious waiting time with the infectious period. And it's exactly due to this bus waiting paradox that if your model is ODEs, if you're thinking about everything in terms of boxes and flows, then the infectious waiting time and the infectious period have the same distribution. So that, I hope, was fun. It took a little more time than I expected, and we'll see how far through the talk I get. So most of what I do, I think of now in terms of new words that I coined for this framework called strength and speed. And these are going to be quantities that are familiar to many of you, but which I tried a little bit to rename. So we've learned from our simple models that we expect diseases to increase exponentially at first, that there's a tendency to oscillate. And we also learned from simple disease models that big R has a threshold, right? That we want big R to be less than 1 for the disease not to spread. And I'm going to refer to big R as the strength of an epidemic, and I'm going to use strength in other related contexts. And I'm going to refer to little r as the speed. And big R has a long history. Big R is a movie star. Kate Winslet talks about it in Contagion, and you see it a lot on the front pages of newspapers during COVID. And it goes back to an insight of Ronald Ross over 100 years ago, which is that big R has a non-trivial threshold. That if you were to reduce the average number of infectious bites caused by a case of yellow fever to less than 1, yellow fever would gradually decline and possibly disappear from the canal zone. In other words, if you were to start somewhere here on the curve and somehow find a way to get rid of 50 or 80% of the mosquitoes, then instead of reducing yellow fever burden by 50 or 80%, you would reduce yellow fever burden close to 0, because yellow fever would no longer be able to sustain itself locally. R is also very much in the newspapers now because of debates about herd immunity. If we have R new cases per case when everyone is susceptible, then if immunity builds up into the population to a point where that is reduced, if the strength is R and we can reduce the strength by a factor of R, we expect the disease to reach an equilibrium if it's still spreading, or we may be able to control or eliminate the disease. The speed of the epidemic is measured is used little r and the conventional exponential framework. It's the rate of change over the amount, and we get an exponential for reasons that I don't need to explain to you. And I like to think about, instead of the doubling time, the characteristic time, which is a little bit longer than the doubling time. And very often in a noisy world, if we have a new disease, we can get a good estimate of the speed even when we don't have a good estimate of other disease parameters. This happened with HIV. Some people would say it's still happening with HIV, that the best thing we understand about is the initial speed. It happened early on in the Ebola epidemic. By the way, when HIV was first analyzed and C was found to be 18 months, that was faster than anybody expected. And when I found out that Ebola's characteristic speed was 1 month, that was slower than expected. And that's interesting too, because it reminds us that really nothing is fast or slow. No time scale is fast or slow, except if you can compare it to another time scale. And in this case, what we want to compare these growth time scales to are generation interval time scales, the generation interval that I took from the infectious kernel. And here's a picture from coronavirus, which has, in fact, a very short and very frightening initial period of growth. So what we see clearly for coronavirus is little r is the speed, but people, especially back in March and April, weren't even talking about it. By May, people started talking about doubling times, but when modelers stepped in, we started calculating big R right away. And so for the rest of my 45 minutes, I'm going to talk first about how we do this, but I'm also going to take a short detour into why we do this and ask whether big R is overrated as compared to little r. So how we do it is implicitly or explicitly by using generation intervals. And almost any calculation people use to get from speed to strength can be reframed as a generation interval calculation. The generation interval is a distribution of times from when I get infected to when I infect you. And I would say that generation intervals are the poor relations of the disease modeling world. People often just pull them without questioning much. And really, when somebody started probing me about the behavior of the generation intervals a few years ago, Neil Hens, when he invited me to Belgium, it's changed my whole life. Like everywhere I look now, I see generation intervals. So here's a generation interval, just to be clear. This is an approximation for Ebola, and what it's showing us is that if I get infected with Ebola, I'm very unlikely to infect anybody else in the first few days. Notice these densities have to be multiplied by the number of days and not by the number of bars. Between 10 and 20 days is when I'm most likely to infect people. And here again, I've tried to interrupt myself. I'm not sure if I'll demand verbal answers, but I want to ask, if I found out that Ebola is actually faster than this, or if I found out that coronavirus actually has more pre-symptomatic transmission than I thought, is that good news or is it bad news? Or quick disease generations in this sense, short within individual process, is that better or worse? Is that more dangerous or less dangerous? Maybe we should ask people to put their thumbs up for less dangerous and thumbs down for more dangerous if we found out there's more pre-symptomatic transmission. And hopefully I've at least gotten you to think about whether you would do that. And I can also reveal that I'm going to claim at least that there's no wrong answer to that question, that whether the effect of quickness is conditional on what you think you already know. If I already know how many people you're going to infect on average, if I already know big R, the strength of spread, then quickness is obviously bad news. If you're going to infect on average 3 people, the faster you're going to do it on average, the worse. But conversely, and really conversely in the sense that there's a direct link between these two, if what I know is the speed, then your quicker behavior doesn't change my estimate of the population level spread, because I already think I know it. It changes the number of people you need to personally infect. If you're doing it faster, you don't need to infect as many to get the disease to spread as fast, right? So this seems counterintuitive, even though it's almost equivalent to the first paragraph, which is absolutely intuitive. So here we have a slow disease and a fast disease, that is within individual scale. If they're spreading at the same speed on the population level, it means that the generational strength, the number of people I need to infect in one generation to achieve that speed, is lower if the generation is longer, and oh my God, lower if the generation is faster, and higher if the generation is longer. So whether more pre-symptomatic spread is good news or bad news in coronavirus in particular is going to turn out to be a very complicated question. But this should all make sense. The speed at the population level is really a product, in some sense, of the two things that we're thinking about at the individual level. The quickness, how quickly does the disease develop within you and spread to somebody else? And the strength, how many people on average do you spread it to? And the strength is sort of a quotient. More quickness implies less strength if the speed is known. And there are cases where we really have good direct information about the speed, like HIV in the end of the last millennium. We had much better speed than strength information. Or if we're going to look at, say, measles from the middle of this century, we don't get any sense of the real intrinsic speed of measles from these spikes because we never get anywhere near a totally susceptible population. But we can use information about a circulating endemic disease to estimate strength. So what's the link between speed and strength? There's some really simple calculus that many of you will have seen. If we assume that S is staying roughly constant, and it doesn't have to be 1, we can fold it into this K, but the Euler-Latka equation says the rate of exponential growth is what it takes to balance this equation, so that if we discount future contributions so that we preserve the shape of the time distribution. I should avoid the temptation to try to explain that better. We get a very simple equation. We factor capital R out of our kernel, and if we can estimate little r, and if we can estimate the generation interval distribution, then we can estimate big R. And note that this factorization, okay, we're not going to note that. We're just going to keep going here. So here's an example for Ebola of, I guess I should have noted it. This is my estimated kernel, and this is how much I would have to discount the kernel in order for it to be a distribution. And this corresponds, as we'll see, to one kind of measured generation interval. The classic way to write this, somebody presented it yesterday and was talking about how beautifully simple this formula is. This is a generating, basically this is a way of writing this in generating function notation. People use this generating function to calculate big R. I find that for most people, it just makes big R seem like this mysterious black box thing. And I prefer to think about it more concretely. And I've given whole talks about different intuitive ways of thinking about the timescales, but I'm going to try to get through one part of it in about 3 minutes, which is that we can approximate and or interpret the relationship between little r and big R by saying if we know the mean generation interval times the rate of spread and something about the shape of the generation intervals. And the something about the shape is related to the CV squared that I showed you earlier, but not exactly. It's if your model is an ODE model and your distributions really come out to gamma distributions, and this kappa is exactly kappa. Otherwise, I sort of define it to make the equation work, which is maybe cheating. This equation may appeal to some of you. It's the compound interest approximation to the exponential, so that as it starts as linear and as we increase 1 over kappa to 2, 3, 4, or infinity, it's like what you would get if the bank compounded your interest more and more. So it looks kind of like this. So if we assume, so here I've put the product of little r and capital and the mean generation interval. So basically, if we take the ODE assumption where everything is exponentially distributed, then we get a linear relationship between our estimate of little r and big R. In the other extreme, where generations are absolutely fixed, we get an exponential distribution. And we have a paper where we explore this approximation. So what I'm showing here in black are 3 examples of the compound interest approximation, the two that I told you, and one that's fit to an estimate of the generation interval. In blue is a much more detailed simulation calculation that's probably a little bit closer to the truth, but not very far from black. And the points are things that were estimated by a third method by a group led by Corey, and presumably using methods similar to those some of you have heard of that Corey et al. And Epiestim are using now for COVID. And what we see really is that just little r times g bar is not sufficient to get a good estimate of the link between speed and strength. But if you have a single shape parameter, you can do a pretty good job. The other thing we've done with this is we've asked what happens if you try to propagate error. So this is an analysis we did of early estimates of big R from the COVID outbreak. And here is a combined measure of uncertainty about big R based only on uncertainty from little r. This is based only on uncertainty from mean and shape of the generation interval, or if you combine them all. And so thinking about it in this relatively simple way is what gave us the tools to ask, can we propagate error? And as we go forward in time, as little r gets better constrained, we see it becomes more and more important to include uncertainty in the generation interval. Okay, so generation intervals are really important, and you've heard people talking about generation intervals or transmission intervals more generally, which includes serial intervals, which I'll get to hopefully soon. And really, as I said, this is to remind me to tell you the story I said before, that when all you have is a hammer, everything looks like a nail. And right now, my hammer is thinking about transmission intervals, and everything I see, all the disease modeling questions I see look to me like nails. We've done some thinking about, so the thing that started me on this was the fact that generation intervals, which until a few years ago I just threw into my disease models without thinking, when you try to measure them, they get very slippery. So we can estimate generation intervals by observing people. How long do they take to become infectious? How long are they infectious before? For what titers do they have? What's their gametocytemia, or how much flu do they have in their nose? Or we can estimate them by contact tracing. Who do we think infected whom? When do we think they got infected? Or, as we know from COVID, we may be easier to ask people when they got ill than to try to figure out when they got infected. And not only do these things look different in reality, but they look systematically different even in simple simulations, which is something that surprised a lot of us over a number of years, and which I think has been sorted out. It was largely sorted out, if you read the papers carefully enough, before I got there, but many disease modelers hadn't caught up or were having trouble interpreting these things. But you can observe these anomalies even in simple models, that the contact tracing intervals look different depending on when you observe them, and also look different from intrinsic. I guess if they look different from each other, they have to sometimes look different from the intrinsic ones. And so we tried to think about, what do we mean by an intrinsic interval? And we could ask, how infectious is a patient at a given time? But we could also ask about forward and backward intervals, which might naively seem to be the same thing. And in some sense, forward and backward intervals are all the same things, because every interval has a start point, which is when I got infected or symptomatic, and an end point, which is when my victim got infected or symptomatic. But if you group things together in a particular time, these can look quite different, and they can look quite different for an easy and easily interpretable reason once you start thinking about it. And what's that reason? Well, here is my HIV curve. And if I say, here's somebody who got infected in 1994, and I'm going to ask, well, how long was a backwards generation interval for this cohort, the answer is not very long. The person who infected this person got infected probably 2 or 3 years ago, definitely not 5 years ago. Why? Because nobody had HIV in this country 5 years ago, or virtually nobody, right? So there's a bias to when the infectors are available. Conversely, if I look forward from 1994 and 1995, not much was changing, and my forward infectious interval is likely to be very similar in this case to the intrinsic one. How infectious was I through time? And of course, other things could be changing through time. But even in a simple model, we expect backwards generation intervals to change for that reason. And even if I took everybody, so I can look at it from a cohort point of view or from a censored point of view, meaning I'm going to limit myself to all the cohorts that would have been available to somebody studying at a particular time, we get a very similar answer. And we can show from simple simulations that the theory almost exactly matches what you get from simulations, that we expect backward intervals to be short at the beginning of an epidemic because there's nowhere to look back to. We also asked about spatial effects and how do local interactions affect realized generation intervals. There was a paper that had a big impact on me that came up with results that again seemed counterintuitive, but aren't when you look more carefully. If I'm embedded in a spatial network, if I imagine I'm interacting more with some people than with others, compared to a homogeneous world where I'm equally likely to interact with somebody across town or across the world as with my neighbor, what happens is there are more wasted contacts. I'm going to contact you, I'm going to infect you with the flu after 2 days, I'm going to contact you again and make a contact that would have infected you with the flu after 4 days, but that contact doesn't count because you already got the flu the first time. So local structure shortens generation intervals and is going to lead to smaller estimates of R if we're using observed generation intervals. And so we made a structure where we tried to think about what happens if we're observing infectiousness. And if we're observing infectiousness and then trying to apply it to a real population, we need to do spatial corrections. And here it shows there's a simple spatial correction like the one I told you about, which you can sort of do. And there's a network-based spatial correction, which can get extremely complicated. Conversely, if we observe actual contact pairs in a spatial network, that's magically taking care of the spatial effect for us, but we do need to do a temporal correction. And we found that this all basically works not only as we expected, but really better than we expected. So if you measure individuals and you can try to do a spatial correction and you can get reasonably close to the empirical R0. So these are all based on simple network simulations. If you do contact tracing, your initial estimate of R0 can be really quite lower than the real value, but the temporal correction gets you really right into the range, although there are questions here with stability. So those are issues, even just with generation intervals. Observing generation intervals and putting them into your model is hard, but not nearly as hard as the reality that for most diseases, we don't observe generation intervals at all, or even really try. We're really often focused on serial intervals. So here we have some dogs biting other dogs. The generation interval is the time from when this dog was infected to when it infected another dog. In rabies, we can observe that, right? Because the dog typically bites the other dog in a localized time span, whereas for things like coronavirus, people don't even tend to try to guess when exactly you were infected. There might be exceptions to that. A serial interval is the time from when the first dog shows symptoms to when the second dog shows symptoms. And you've heard a lot about serial intervals in the context of coronavirus, but getting from serial intervals to generation intervals is harder than you think. You might think, and a lot of people start by thinking, that they should have exactly the same distribution. And there certainly are simple assumptions you can make that are reasonable in some cases, which lead to the conclusion that they do have the same distribution. On the other hand, there's a simple and dramatic story that you can tell to convince yourself that they can't always be negative. If I infect you, I must have gotten infected before I infect you. But if I infect you with, say, influenza, it's very possible for you to show up in the medical records before I do, which corresponds in every important way to a serial interval that's negative in time, whereas a generation interval can certainly not be negative in time. And it's useful to think through what are some of the reasons that can make these distributions differ. But until a few years ago, we thought that if you regiment the infectious process so that symptoms always start before infectiousness, then we really do expect this serial interval to equal the generation interval. The serial interval is, sorry, this looks like the generation interval. I get infected, how long until I show symptoms, plus how long, if any, until I become infectious, plus how long it takes me to infect you. And the random variable serial interval is the sum of the same three random variables as the random variable serial interval. And so certainly in a simple model, I think I just said something wrong, but hopefully you all understood what I meant to say instead of what I did to say. It's easy to make a simple model where these distributions are the same. And we were working on that assumption for years and years with rabies until Mike Lee actually tried to do a sanity check when we finally had enough good data. And we found that, in fact, the measured generation intervals, observed generation intervals, tend to be much longer than serial intervals. And how is this possible? It's because of heterogeneity in the population, in the way they react to disease and in the way they behave. A generation interval is the incubation period of a biter times the infectious waiting period of a biter, somebody who gives somebody else the disease. And the more I bite, the more times this incubation period is counted. A serial interval, on the other hand, is made up from exactly the same infectious wait times, but it's made up of incubation periods from a different set of dogs. And if that different set of dogs, if the dogs who bite less have systematically different incubation periods, then what we're going to see is here's a dog, which might be a particular kind of dog with particular tendencies, that bites once, and its incubation period counts once. This dog's incubation period counts 3 times. And what we found is, yes, indeed, there is heterogeneity in the dogs that's exactly consistent with what was this really surprising difference in between the observed serial and observed generation intervals. So that's one problem with serial intervals. Another problem is that the whole forward-backward censorship things becomes much more complicated with serial intervals. And this is something that plagued me for quite a while. It's Daniel Park took the lead in really working out this paradox, which is that we could imagine that we don't know anything about infection. You know, that somebody has symptoms and then somebody else has symptoms, and we could imagine a renewal process, which is not the real physical renewal process, but which should have the same mathematical properties, where the symptoms in the infector cause the symptoms in the infectee. We're going to assume that hosts are homogeneous. And the serial intervals, this fictional process, has the same dynamics as the real process. So we should be able to do the same calculation. But in fact, in general, we expect serial intervals to be broader than generation intervals because incubation periods, the time until I show symptoms, are not exactly the same as latent periods, the time until I become infectious. And that creates additional uncertainty. And we know, even though I was going too fast to explain it, we know that a broader generation interval leads to faster spread for a given value of little r, which means that a broader estimate of the transmission interval should lead to a lower estimate of little r. So this is a real paradox because the disease is doing what it's doing. We should be able to describe it consistently with these two different mathematical frameworks. And the answer to this paradox is pretty amazing. What it is that unlike the generation interval, where when you're spreading exponentially, the forward generation interval, the thing that's physically driving the disease, is equivalent to the intrinsic generation interval, which it sort of has to be because this is the physical process by which the disease is spreading. That's not true for serial intervals. A serial interval is a sum. Basically, if I get infected here, if I show symptoms here and I infect you and you show symptoms here, that's a sum of my incubation period going backwards. I look backwards to ask when did I get infected, and then I look forward from there to say when am I likely to have infected you, and then forward again to say when do you show symptoms. Your showing symptoms from the time you're infected involves only you. There's no dynamical reason for that to change. The time from me getting infected to infecting you also is not directly infected by the dynamics during the exponential growth period. My intrinsic tendency to infect people is going to drive that. But the backward incubation period is affected by disease dynamics. If I know that I showed symptoms on Tuesday, the time I got infected, my estimate of the time I got infected depends on how infectious the environment was in the past. So fast growth actually shortens the backward incubation period, I hope, shortens the backward incubation period, lengthens the generation interval, and makes everything balance perfectly. So this was a lot of fun. Here's a picture using COVID-like dynamics. The forward serial interval that drives the disease is a result of the generation interval, which doesn't change much. The forward incubation period, I'm sorry, I'm talking very fast and I've already used my 45 minutes and I have no idea what to do about it. It's 45 minutes just now. For those who joined late, we also started fairly late and I am trying to be good about time. So here's the forward distributions, backward distributions from a reasonably detailed, reasonably COVID-like simulation. And we see the backward incubation period is lower than the intrinsic incubation period for the reason I said, that if I show symptoms on Tuesday, that has something to do with how long it takes to show symptoms, but also something to do with how likely it was I got infected on any particular day, and it all balances perfectly. I got through these two sections exactly as I expected, and this one took more than twice as long as I expected. So I will try to get through the last third of my talk in 3 minutes. No, 4 minutes. I was told 45 to 50 minutes of talking. So I said I was going to talk about how we link strength and speed. I'm basically done with that. And then the question is why, and my answer to why briefly is because it's a thing to do and it's driven by history and we shouldn't do it as much. And in fact, the whole strength paradigm that R is greater than 1 and that we can basically measure how strong an intervention is and is it strong enough to balance the strength of the spread of epidemic and eliminate the disease. The whole strength paradigm has a parallel speed paradigm. Little r greater than 0 is also a threshold. It's a less interesting threshold to a mathematician because it seems trivial, but it's a threshold. There's a interesting and non-stupid way to measure the speed of an intervention. And it turns out that just like some diseases are easier to observe. I'm skipping a lot of stuff on purpose. I apologize. The slides are up. Just like it's easier to see the speed of HIV, but the strength of measles, that's true for estimating interventions too. So if we're vaccinating people against measles, I would call that a strength-like intervention, because we're saying we're going to reduce the total risk in the population by a factor of 2. Whereas if we're encouraging people to come in frequently for HIV testing, this is Bishop Desmond Tutu publicly getting an HIV test, and then treating them once they become HIV positive, that's much more like a speed-like intervention. We're not reducing it by a given factor for everyone, but in fact, we're reducing the, what's the word? Oh my God, realized infectiousness of infected people through time. And so the strength and speed paradigms are equally valid, and they help us understand answers to things like my COVID question. So here, using the speed paradigm has substantially clarified the interpretation of results about what it takes for a test and treat program to work. Doesn't change the results. The underlying math is all the same, but it helps us interpret it biologically and maybe more easily see whether we can trust it. We can also ask a similar question about COVID. And I asked before, if there's more pre-symptomatic transmission than we thought, that sounds like bad news, but it could be good news or bad news. In particular, if we're thinking about doing things like masking, just reducing contact at the population level, it's not bad news because we already know the speed of the invading epidemic. So that's not changing with more pre-symptomatic transmission. So if we're looking at it from a speed-like framework, it's not obvious whether it makes things better or worse. But if we're looking at things from a strength-like framework, more early transmission is better. If we're looking at it from a speed-like framework, you can actually do a second-order thing about when it would be better or worse, which I'm not going to get into. Finally, people spend a lot of time asking, well, are things getting better or worse now? And I showed that scary picture from Ontario to lead off. And there's a lot of issues here. The main issue is that the data are extremely complicated, but don't include infection dates. Deconvolution is hard. Dealing with data messes is hard. And these things are really practically important, because what we're doing now is looking at different interventions and asking whether they worked. And that's typically done by estimating big R through time using one of these two paradigms, either instantaneous, that is to say, if I froze the conditions now, how many people would each infected individual infect, versus the case reproductive number, which I forgot to write text for, but that's basically asking somebody infected now, there's serious typos here, I apologize. Somebody infected now, how many people do we expect them to infect? And people applied originally these two methods to incidence data from Wuhan, and one group found that the lockdown worked really well, and one group found, as pictured here, that the lockdown worked less well than expected. Both groups did it on symptom onset date. Neither group at first tried to deconvolve. And so there are a lot of hard questions about how to deal with the real data, but we also have a relatively new insight that doesn't solve the problem, but I'm going to end the talk with it anyway, which is that all of these methods are assuming the generation interval doesn't change through time. The kernel is changing in some sense as the product of a fixed generation interval and a changing value of R. And this turns out to be a good match for strength-like interventions, but a bad match for speed-like interventions. And in fact, you can't always tell whether all the things you're doing are strength-like or speed-like. You can't tell them at all from the incidence data. It's completely statistically and in fact, mathematically unidentifiable. But what we found is that if your intervention is strength-like, and if you can find incidence of infection, which you can't always do, then using the Corey instantaneous big R is the best thing. Whereas if your intervention is more speed-like, you get the best estimate of effectiveness just using poor old neglected little r. And I'll say I'm excited about these results, but they don't solve the bigger problems in application, which is how to deal with these messy information about delays. I'm very sorry for going over time, and I would like to very much thank all of you for your attention, and to thank everybody on this slide, and probably a few people who should be on this slide and aren't.
Okay, let's all unmute for a moment to give Jonathan a round of thanks for that talk. And as the hour is getting late, let's take one pressing question right now, and then we'll take every other question over to the GatherTown chat spot. Erica has just put the GatherTown link up into the chat. So do we have one question for Jonathan before we disperse?
Yeah, well, I'll jump in there. There's been a lot of discussion about super spreaders versus sort of more low volume numbers of follow-on infections. So when you have tremendous variability in the number of folks that you're going to infect, how does that play into this kind of thinking?
Yeah, that's a very good question. On average, it doesn't. I mean, all this stuff still works. This stuff in practical cases doesn't necessarily work very well anyway, because there's a lot of possible sources of variability. So the answer is that in theory, it still works. In practice, it becomes harder. What we should have but don't is a way to try to widen our confidence intervals still further, which is funny because my confidence intervals are often wider than everybody else's, and I'm often trying to make them wider when I have my science hat on, and then very often I have to make them narrower for, you know, a public health person who I like, who says I cannot show this to the next people up the chain, and you're not allowed to try to convince me why I should be able to show them because they're busy and I can't. So I spend a lot of time widening and narrowing confidence intervals, but I think that's the only answer I have. It's yet another source of uncertainty with no easy way around it.
Thank you.
All right, then thank you very much, Jonathan.